Now we turn to two everyday questions. Who are a vertex's neighbors, and does one specific edge exist? Let's see how each representation answers them. Both forms answer the same question. Who is adjacent to vertex U? But the cost is very different, especially on a big, sparse graph. This slide shows the matrix version. Print Neighbours matrix. It loops V from 0 up to G arrow in, so it visits every column in the row. For each column, it checks the cell G at row U column V. If the cell is 1, it prints V, but it still touches all n cells, even the zeros. Here is the list version, print Neighbours list. It walks the chain at edge of U, following E arrow next until the pointer runs out. For each node it prints E arrow to. It touches only the real neighbors, which is degree of U nodes, and never sees a 0 at all. For vertex 2, both versions give the same answer, the set 0, 3, 4. But the matrix touched all 6 columns to find them, while the list touched exactly 3 nodes. So neighbors on a matrix is big O of n, and on a list it is big O of the degree of U. Try the learning check. List the neighbors of vertex 2 two ways, by reading the matrix row and by walking the list chain. Do the two answers match, and which one did less work? Pause here. Here is the answer. Both give the set 0, 3, 4. The list walk did 3 steps and the matrix did a 6-cell row scan. Same answer, half the work. The matrix wins clearly in one place, testing whether one specific edge exists. Has edge matrix takes the graph and 2 vertices, U and V. It just returns the cell G arrow matrix at U times G arrow in plus V1 direct lookup, big O of 1. Has edge list does the same job on the chain. It walks U's chain, following E arrow next until the node is null. At each node it checks if E arrow 2 is equal to V. If so, it returns 1, meaning the edge exists. If the walk ends without a match, it returns 0. So the list may scan the whole chain, which is big O of the degree of U. So for has edge, the matrix is big, O of 1, and the list is big O of the degree of U. This is the one operation where the matrix has the stronger worst-case guarantee, no matter the density. The list may need to scan up to the degree of U nodes.